Okay, I think we're up and running. So the next little thing I want to do is prove that two resistors in parallel, or rather work out what the result of two resistors are in parallel from first principles. So let's just have a statement of what that problem is. So we're going to assume DC. So we've got a voltage in, and we have two resistors going into ground. It's quite important actually in multisim that you do connect that ground symbol on the bottom. More on that as we come along. Now, what do we know about the circuit? Well, we know that this is a resistor, so we're going to call it R1. This is another resistor, which is a different resistor, so we're going to call it R2. We also know that we've got a voltage, an associated resistance, so therefore we must have a current. And it seems reasonable that that current at this point here is going to split, and I'm just going to call this little I1, and I'm going to call the current flowing through here little I2. Okay, so you can all see that pretty well. I can see it on screen. Now what we're trying to do is we're trying to derive a formula which tells us what the total resistance is of two resistances in parallel. So let's have a look at what we know. So one of the things that we can know is that I1 is equal to V in, which we're just going to call V. I'm just going to cross that out because there's no V in or V out here. So just going to call that V. So I1 equals V upon R1, and I2 equals V upon R2. Nothing earth-shattering there at the moment, and also we know that the current flowing here must equal the sum of these two currents here. Why? Well, because Kirchhoff's current law states that current entering a junction must equal the current leaving. Statement of the obvious really. The current which is coming in here into this junction here must also leave that junction, because otherwise you'd have an accumulation of current there, which would be quite a strange concept. So if we acknowledge that Kirchhoff's current law is correct, which I'm sure it is, then that means that this big current here is actually just equal to these two little currents, I1 plus I2. Nothing terribly unreasonable there so far, but also we know that I1 is this and I2 is this, so therefore we can now write that I is equal to V upon R1 plus V upon R2. All we've done is we've put this into here and this into here. Again, nothing particularly earth-shattering. Now, a very simple piece of algebra. So what I can do is I can pull out the V, and I end up with 1 upon R1 plus 1 upon R2. Okay, reasonably straightforward. Now there's a special case with two resistors. I'll show you in a minute where you've got many resistors in parallel. But for the case where there's two resistors, what we can do is we can use a technique called lowest common denominator, high school mathematics. And what we can do is we can try and change this so that we don't end up with two fractions added to one another. So the lowest common denominator is R1, R2, and if I multiply that one by R2, I need to multiply that one by R1, need to multiply that one by R2, so we end up with this as directly equivalent to this. Well, we need to put the rest of the equation back in. Okay, so far so good, nothing earth-shattering there, we just used our lowest common denominator. Now if we rearrange that, we can take the V across here and we end up with I upon V is equal to R2 plus R1 all upon R1 R2. But I upon V isn't very useful. It would be more useful if it were V upon I, because V upon I, we have I upon V, remember, but V upon I would just simply be the total resistance of the circuit, which is what we want. We want R total, the combined resistance of that circuit. So to achieve that, all I've got to do is actually turn that upside down. It's the easiest way. And if I turn that upside down, I also have to turn this one upside down. So R total equals V upon I, which equals R1, R2 upon R1 plus R2. That's really neat for two resistors in parallel, and generally you only usually have two resistors in parallel, so that's a beautiful, beautiful formula which will give you the combined parallel resistance. Okay, nice little demo there, just showing that what it shows in fairly elementary textbooks is perfectly correct. Okay.